Oh, I think let's start. People will people will join. Let's start now.
Yes, sir.
Now, yeah, Vandana, yeah, please.
Uh, Good evening, everyone. It is my pleasure to welcome you all to today's webinar on digital twins, the future of smart food processing, organized by H&M Food Pro Academy. A warm welcome to our host, Professor H.N. Mishra, Emeritus Professor, Founder H&M Pro Academy, and Dr. Arpan Dubey, our speaker, and all the participants joining us today. As the food industry is becoming increasingly digital and data driven, technologies like digital twins are opening up exciting new possibilities for smarter and more efficient food processing. Today, in this webinar, we will explore how this technology can shape the future of the food industry. Before we begin, I would like to briefly introduce H&M Food Pro Academy. Academy is dedicated to providing industry relevant training, internships, research, industrial consultancy, entrepreneurship support, and career guidance with the aim of empowering and developing future food professionals. It is now my pleasure to introduce our speaker, Dr. Arpan Dubey. Sir holds PhD from IIT Kharagpur, where his research focused on composite millet-based bread using ohmic heating technology, including system design and computational modeling. Sir has contributed to several international journal publications and presented his research at national and international platforms. Post PhD, Sir started working as a design engineer at the Nutrition Innovation Hub IIT Kharagpur. Currently, Sir is working as a postdoctoral research associate at IIT Kharagpur. With his interdisciplinary background in food processing, computational modeling, and emerging technologies, we are very pleased to have him with us today. Sir, I now invite you to take us through the today's session. Over to you, sir.
Yeah, thank you very much, Vandana, for such a nice introduction. So without delaying, I'm starting my presentation. I'm sharing my screen. Hope my screen is visible.
Yes, sir,
Yes,
it is visible.
go into the presentations. Yes, fine.
Yes. So a very good evening to one and all present in this webinar. Today, we are going to learn about digital twins, the future of smart food. So before beginning our webinar, I'll let you briefly conceptualize the idea of digital twins. Now, imagine there is a food factory that is working all day throughout, and it has its own brain. Okay, so the factory is working with various processing operations, and during the processing, we are monitoring the operations. We are getting data from various sensors. Now, if we have a digital brain, what it can do is it can take the data from these sensors, analyze it, understand it, and can use the data in order to predict and give a better quality and a safe product throughout its manufacturing journey. So this is a brief gist how this concept has come to the industry of digital twins. Okay, so a human brain is limited to limited functions, but a computer can handle multiple functions with higher efficiency compared to human brain. So this is the idea how we can replace human intervention in industry and make it more efficient and get good quality products in food processing industry using this technology. Now, if we have such brain in a food industry, what should be its function? First, it should sense the data. So whatever the data, whatever the sensors are giving output of these sensors, this brain can sense. The second, apart from sensing, it should not just show the data, it should understand the data. So like just like human brain, it can interpret the temperature is high or low, like these type of things. After understanding, it should make some rational prediction that whether this data can be like the process is going in some right direction or not. Okay. Once it predict, it can optimize. So Once the data it analyzed, it predicted, now it can think, okay, I will twitch something, I will go on to correct something like this, this voltage or this pressure, so that the final product will be in good quality. Once it optimizes, it should also act in direction to do something. So this is the basic fundamental function of the brain, which we are going to have in our factory. Okay. So if you get this concept, this is nothing but a concept of digital brain, and this is called a digital brain, digital twin. Okay. So now we will build our concept more briefly. Coming to the timeline of the digital twin technology. First, it started with NASA exploring the moon and space. So they don't have such resources so that they can waste multiple material and sending them to space and learn with each experimental thing. So they started making digital twins. So whatever the spacecraft used to go, it goes for analyzing the data, and the same environmental condition they was having a experimental setup inside their laboratory. They used to simulate such things like what is the pressure, what is the temperature, and through this they used to understand what kind of mistakes they can make when they are exploring space and all. Now, with evolving concepts and technology, the first brief conceptualization or birth of digital twins came in 2002 and 2003, when it was used for product lifecycle management. After this white paper, it goes on evolving, and into around 2010 and 12, NASA start again experimenting with these digital twin, but in much more depth. So even a simple or a very intricate type of physics can be simulated, and their spacecraft or their technology can be space proof. After this, in 2012 and onwards, this explosion of computational power with AI and data centers, it has converged to different zones. So every industry is now switching to IoT-based, AI/ML-based, optimized, efficient industry. So this is how we have progressed in digital twin technology. Okay. So once we progress, we got to have various definitions, but all these definitions are like just words put into some sentences. But the real definition, you can build it of yourself once you understand the concept. So let us, as a food engineer or a food technologist, understand how the things works and what are the fundamentals of a digital twin. So let us suppose we have kept milk for boiling on a stove, and we switch on the stove, and we have some sensors that can measure the temperature. Okay. So while measuring the temperature, all throughout the process from initially heating to the boiling, we record the temperature. Now, what we do is we take our computer, we take some simulation software like ANSYS, COMSOL, we model this physics into our computer, get this physics validated with the sensor data we just used during the cooking or boiling of the milk. But you see here, the data is already recorded in this scenario, and we are now validating this results after simulation. So this type of simulation is called digital model. Okay, so there is no integration between the physical layer and the digital layer. All of the information has been recorded previously, and we are now using it to build a model. Although this model can be further used to simulate various conditions. If we change the dimension of our pot, or we increase the temperature of the stove initially, what will happen? Our model can predict it. But there is no connection between real-time data and the data which our model is predicting. So we can go a step further, and suppose in the same condition, we are having a pot, we kept the milk for the boiling, and since the milk is boiling, we are recording the temperature. We have already built that model with us, the model is with us. We are now recording the temperature, and we are real-time transmitting the data to our computer. Now, what this model can do is, given your heat sensitivity of your oven and stove, it can predict how much time it will take for milk to boil. Okay. So there is a dynamic unidirectional flow of data. We are actually monitoring the process in real time, but although the computer is predicting our temperature or the time at which the milk will boil. But this is called digital shadow because there is still a separation in the physical layer and the dynamic layer or the digital layer, because we are feeding the real-time data, but this real-time data is not going to our physical system as such. Now we will go a step further. In this setup, if we put the pot again for boiling, now we are recording our temperature. We have already built the model. We are recording our temperature in real time. And this is transmitting the data in real time to our computational model. And our computational model itself is now transmitting the data back to our stove that is connected with some sort of actuator that can regulate the stove heat sensitivity. So based on your time requirement, you can ask the computer, I just want to boil the milk in less than 10 minutes. So it will regulate the heat stove accordingly, and without your interruption and without your monitoring the process, it can boil the milk. So there is dynamic bidirectional flow of sensor data. Here, the data from the sensor first go to the simulation software. The simulation software analyzes the real-time data, makes an informed decision, and goes back to the actuator that can act on the data it has predicted. This is nothing but a digital twin. So in digital twin, there is an integration, there is a connection in physical layer and the digital layer. So we have seen all the parts like digital model, digital shadow, and digital twin so far. Now in digital twin, what are the main components what we can access from this simple example? First, we should have a physical model and some sensors to measure this physical activity in the food processing. Secondly, we should have some data transfer and computational simulation capabilities to analyze and predict the future conditions. Next, we should have some actuator and controllers in order to control the situation, or we can make some informed decision without human intervention. So since we have seen the concept of digital twins, let us now begin to know the building blocks of digital twin. Okay. So basically, digital twin is based on physical model. So we need a physical model, right? So in any food processing operation, it might start from a post-harvest operation. After post-harvest operation, there is transportation. Then there is food processing, obviously. And after, once the food is processed and packed, there's packaging and storage. And then we transport the material to the end customer itself. Now here it gets interesting. We don't need to build the model for each and every process. Okay, we have to see what is the bottleneck of the whole processing atmosphere. So it can be transportation. In case of some ice creams and all, there is very important to maintain temperature during the transportation. Whether it can be as fresh produce after just cutting and processing it, we want to transport it as easily and as conveniently as possible. So identifying the bottleneck of the process is really important in order to build a digital twin. Okay, so based on these physical conditions, we can start building our digital twin. Then comes the sensors. So obviously, since we are measuring the quantity in real time, we need some high-end sensors so that our data has good fidelity, and we should have good command over the prediction which we are going to make based on the data we are getting. So in basic food processing operations, there are temperature sensors, there are pressure sensors, there are level sensors, flow sensors, moisture sensor, gas sensors, and optical sensors. So these sensors give you different physical properties that you can analyze and predict based on these analytical properties. You can predict the using our computational model. Okay. Apart from this, we can also have some 3D laser sensors. These are quite good and new high-end sensors. Like 3D laser sensors can measure you the depth and the volume of the product, shape of the product. NIR-based sensors can measure the moisture content without distracting the product. Hyperspectral sensor can give you molecular level information using the hyperspectral, the range of infrared wavelength. Once the data is collected, another important thing is to communicate the data. Once we get the data from the sensors, we need Wi-Fi communication, we need RFID communication, so that the informed, like the data which we have got in real time is got to be transmitted to our computational model. Apart from this, we need microprocessor and SBCs. Like SBCs is a single board computer. So like Raspberry Pi, Arduino, we need such microprocessors in order to handle this data and conveniently transfer this data. So these are some sensors and transfer models which we can use. Once we get the data, we need to transfer it. So transferring data is contained in different layers. Okay, so first we have sensor layers. So it is called edge layer. So it is the data where it is getting generated. So it is the voltage of some sensor where it is getting generated. Second is the fog layer. It is the intermediate layer. So if you're getting sensor data from around 10 and 12 sensors at a time, you don't need such data for getting a computational model to work. You might require 2 or 3 important data out of that. So this intermediate layer works as a filter where you can filter out what data you actually need in order to get a good fidelity of your digital twin. Lastly, there is cloud computing platforms where what we can do is we can run our model virtually. So if we are having a digital twin, you are going to have a big chunk of data. So handling this sort of data in a local PC, it gets difficult sometimes. So for that, we can use cloud computing. And once we get the data, we process it, we run our computational softwares, we can get some information out of it. The next important part of any digital twin is computational models. Okay, so if we characterize the computational model, first type of computational models are physics-based or mechanistic white box models. These are models that works on basic physical laws like heat transfer, mass transfer, kinetics, thermodynamics. Okay, so in this first comes the CFD simulation softwares, which gives you fluid flow, turbulence, properties of non-Newtonian fluids and all. So these softwares are used in food processing operations, like if we are simulating some type of dryer, some kind of baking oven, this type of simulation softwares or some computational models can be useful. Next, there are multi-phase porous media modeling. In this, if some porous material is there, suppose if you are processing drying operation in some food processing industry. So in drying, there is porous media that is involved, and there is also a change of the phase from water to gaseous phase. So there can be multi-scale of model. So if the product from initial stage to final state, if it is changing its form and composition, then you can have multiple scale models. After this, we are having discrete element modeling. In discrete elemental modeling, what we do is we simulate single kernels or grains in order to get the friction, the energy that is going to be dissipated, what is the flow characteristics of bulk. So these kind of property can be done through discrete element modeling. And lastly, we can also go way beyond to the molecular level, where we can do Monte Carlo and molecular docking sort of simulation. Although this is not prevalent in digital twin, but these sort of softwares are present in order to model if you want to model it. Now, the first type of model, which were computational models that were physics-based, although they have a very good quality of prediction, they have high fidelity, because these are actually based on physics. But the downside of using this type of simulation software is this can be very time-taking process, because once you apply the mesh and it predicts value in each node, then it runs and gives you a comprehended value. So it can be difficult to run these softwares in real time. So data-driven models or empirical models, black box model basically can be used. These are some AI algorithms, which like ANN, CNN, which we can run in order to get the output data. So this run quite easily. We give some data from the sensors. We train our AI model, and then it gives us the output data. So there is no physics involved in this. So we cannot say whether the data which we are getting is actually what we are going to get in any actual physical process. Although we have trained our model, but getting a data outside the range we have trained for might be difficult for our model to predict. So now people are focusing more on hybrid or gray box model. What it do is it utilizes good things of both data driven and computational like CFD models. So there are two types of hybrid models or gray box model. First is serial hybrid model. So serial hybrid model, you can assume like in this the whole information is what we get is from the simulation softwares like CFD simulation softwares. The only thing that is not very physically calculative, like microbial growth and all, this we get from AI models. So these both the models run in parallel in series, and once we get the data from simulation softwares like temperature, heat distribution, we use AI model to predict some non-physical, physically related things like microbial growth and all. In parallel hybrid model, what we do is we run mechanicist model like the actual physical model first, and then we train the AI algorithm to reduce the error associated with this mechanistic model. So let us suppose if we are predicting temperature inside a pasteurization plant and it gives the temperature error of about 2 degrees Celsius. So our AI model get to know that if our simulation software is giving us a temperature of 70 degrees Celsius, so temperature can actually be somewhere around 68 to 72 degrees Celsius. So with this, it can manipulate and give us, by analyzing the results, it can give us the actual conditions. So these are some computational models that are used traditionally. Now we have moved ahead and we are now using some improved version of each of them by combining each combining the specialty of each computational model. So first is reduced order models. So reduced order models, to analyze this, to understand this, first we see how simulation software or CFD software works. Okay, so if we have a data from the sensor, we put it in CFD model, it will predict the output, and output is going to be of a good correlation with the actual physical condition because it is actually working on the physics. However, it is a very time-taking process. Okay, so how reduced order model works, we should first understand it through an analogy. Okay, so let us see, if we consider our CFD model just like a professor and a bunch of student can be considered as a sensor that is coming in real time from a sensor during food processing operation. Now, if each student asks simultaneously or to the professor might not be able to answer each one of them quite efficiently. Okay, so what professor do, it assigns a teaching assistant. Teaching assistants, let us say it is our AI model. Okay, now teaching assistant also have some problems with the physics, so he asks them through professor what can be the condition, at this condition what type of data will come. This teaching assistant and AI model is getting trained from professor. Now if the teacher comes, if this bunch of student comes to the teaching assistant can easily help because he has more spare time than a professor which is busy with his all assignments. So in this way we have cut off the process, like we have cut off the time required for a process to work. So this is an analogy from which we can understand reduce order models. So just like from analogy, if our CFD model, if we use AI algorithm to put various conditions, so with design of experiment, we can expose our CFD model to various conditions beforehand, before actually processing, before actually deploying it in food industry operation. And now this model is validated and tested beforehand. So while actually running our industry, what we do is we take that data from the sensors and put it to AI model. Since our AI model is trained on the data which we get from the CFD software, it has good accuracy, and we can get output data, and this output data can be further used in order to make some informed decisions. So this is what reduced order models do. They take the results from the CFD software, they train themselves, and from this training, we can reduce time quite efficiently. So this is how ROMs work. Another type of computational model that is getting good results is physics-informed neural networks. In this, what happens is we get the data from the sensors, and then AI model is trained from the data which we are getting from the sensors. Apart from giving this data directly from sensors for training, we are also giving some physics. Like we are teaching them the model that this is the heat transfer equation and this is how it works. So our model not only knows the data which is coming from the sensor, it also knows what is the physics behind this process. Like if we are heating something, it knows how heat transfer takes place. So while doing simulation in real time, what it do is it analyzes the data, it predicts the data, and it cross-checks with the physics whether the data is physically possible or not, and then predicts some output that can be having a good fidelity. So both these ROMs and twins can be used in industry, because the problem with the CFD is it takes a lot of time to simulate the actual results. And in industry, we don't have such time to, we don't have some leverage to process this data and we get good quality results, because the process is time bound. So here we can cut off our time from hours to minutes or even seconds. So this is how our hybrid computational model works. Now, once we understood how different computational model works, we should also know what is the scale of a model. Each and every problem in food industry might be having different scales. Okay, so we can start with molecular scale or micro scale, where we are actually predicting the degradation of some vitamin or some microbial growth or browning. Okay, then we can also predict some phenomena like heat transfer, mass transfer, multi-scale porous media flow and all. Thirdly, we can also predict unit operations. So we can simulate various unit operations. Like if we are doing extrusion, we can predict the pressure, temperature. If we are doing drying, we can see the effect of RS, temperature in the drying curves. So we can simulate whole unit operation. Apart from this, once we can do it for a unit operation, we can also do it for a plant-wide scale. So each and every processing, starting from the raw material processing, we can do it for grinding, we can do it for cooking and whatnot. Even we can plan how the labor movement will be there, how our robots will move in order to get good results. And then consumer levels. So this is basically, once we sell our data, we can collect some feedback from consumer and we can get to know that whether our product is doing well and what information and what things we are going to change in our processing systems, so that we can get good quality of products. So this is a scale of model. This can be dependent on your process. So it can be as easy as process as we have seen in the boiling of milk. It can be as difficult as making some large scale multiple products. So it depends how we are going to deal with different type of problem. Okay. So since we have seen all the processes, their integrities, but we don't know what are the things we are using in order to simulate. I'm saying simulation. So what are the things that or the softwares that are available so that we can do the simulation itself? So for processing and simulation for steady state dynamic system, we can use like most popular is Aspen, AnyLogic, other software like Super Pro Designer. These type of software can be used in order to simulate various chemical engineering problems. Apart from this, since we are building 3D models, if we are building like digital twins, we can use AutoCAD, SolidWorks, ANSYS, SpaceClaim, and some other software obviously are there, which are available in online or in industry. So there can be some tools for planning and scheduling. These are basically important if you are planning to simulate some condition where you are having some logistics problems, like you are transporting some sort of raw material, or you are transporting some sort of fresh produce from one place to another for selling or for market purpose itself. Then comes our computational fluid dynamic models like ANSYS Fluent, COMSOL Multiphysics, which can actually predict the process like multiphysics processes like heat transfer, mass transfer, their integration, microwaves, and everything physical process, they can be more or less can be used, simulate using these processes. Now, since I've also told that there can be some data-driven models, so we can use Python and G-code in order to do that. G-code are also used for 3D printing and all. Then after this, we can develop a GUI because we, as a human, want to interact with computer someday or other. So we can build some GUI, LabVIEW. Even Python can also be used for building environment in which we can interact with. Then some intelligent platforms like data, like cloud server and their services like Amazon Azure tools, then Amazon Web Services, then NVIDIA. All these tools can be used. So these are basically the technology that is available in order to simulate some process. Okay. So once we know how to build a digital twin, we also get to know what is the softwares or the tools which we are going to use for doing the simulation itself. Now we should know what is the stages of implementation. Okay. So suppose we are trying to build a digital twin for our food industry. First is we have to define a decision boundary. Okay. So decision boundary is very important because in the whole processing line, there can be only one or two bottlenecks of the process that can decide the output of the results. Not all the processes are as important as each other. Okay. So we have to define some decision boundary where we are going to build our digital model. Let us suppose we are having a pasteurization plant. So the heat transfer in the pasteurizer itself is very important. So the temperature distribution inside the pasteurization unit is important. So we can start from that place and now we can build our model. So once we define the decision boundary, we should also establish a minimum value or minimum data which we require to build something. So we should have like a data that is good enough to predict our model. So which data we are going to use, what type of data we are going to use, and how we are going to build our model will depend on the second. This is the second step we have to decide. Thirdly, we have to develop and validate the digital twins. So once we develop the digital twins, we validate it and we try to make it fast because in industry, we need faster results in order to get it going with the pace of industry. Okay. Then we calibrate and validate and synchronize. Once we developed it, we made it faster with our like AI data training. We have made our model faster. Then we validate our model and actually actually employing it that in an industry. Okay. After validating our data model, if it is working fine, what the next step we can do is we can scale vertically or horizontally. So scaling vertically means we can go beyond what we have simulated. So suppose we have simulated some unit operation. We can now go to a certain part of unit operation. So this is called vertical scaling. In horizontal scaling, what we can do is suppose we have only simulated our single unit operation, we can build it for different unit operations. So we can expand vertical or horizontally as well. So this is how we can scale the digital twin. Then we have to actually connect our digital twin to take some informed decision, actually taking some decision that was previously been taken from some or other human intervention. So this is how we build a digital twin, starting from getting the problem itself, then establishing what type of data we need, then developing and improving the model, then actually testing the model in actual physical scenario. Then if we want to scale the model up or down, then we decide. And finally, we use this model to make some informed decision in our food industry. Now, since we have seen all the basic building blocks of computation of a digital twin, starting from the sensors and everything, now we actually try to build a digital twin for our food industry itself. Now, let us suppose we have a smart food factory. So it has various unit operation that is going to take place at one play at one go. Okay. So let us start with raw material processing. So in raw material processing, we can scan raw material for any impurities or adulteration. In this, we can use some data-driven models and sensors like hyperspectral or NIR sensor in order to get the quality of the food itself. Okay, what are the raw material which we are getting? We can analyze it. Once we do that, the second step is we have to identify which of the process in the whole unit processing line, the unit operation that is most sensitive to our product. So let us suppose we are heating some product to some degree. So that process can be streamlined, and this process can be computationally modeled using some physics-based modeling, obviously. And we can also make models like ROMs or pins as we have seen. Just like this, after simulating this problem, we have already analyzed the raw material. We have analyzed the bottleneck of our processing line. Now what we do is, since our product is ready, we can use our digital twin to build some packaging scenario so that we can package and store our product in the inventory very efficiently. And we can also schedule the logistics so that there will be efficient transport of our product from the processing industry itself to the market. Okay. So once we pack the product, we ask the logistics to come and take the product from our food industry. We will also integrate some sensors to our actually transporting media. Like if our truck is transporting, if it is having some type of cold chain, if our truck is transporting some type of data, what is the temperature data, this we can integrate to our digital twin. Okay, so this is sending the data back to our food industry during the transportation. While it is transporting our material, we can use this simulation softwares or the real-time data-driven models to actually tune the temperature inside the truck so that our product don't get wasted during the transportation. This can also be used to schedule at what time the product has to leave for what location. Okay, so once our product reaches to the market, now people are going to buy it. Okay, so our product should have good communication with the customer itself. Here we can use some type of smart sensors like RFID sensors and all to gauge what is the freshness of our product and information like this, so that the customers are happy with the quality of product they are getting. Now, the end phase of our whole operation is to get feedback from the customer itself. So we all know today is the world of social media. Apart from this, we can put a label inside our package so that people can post the feedback like the quality of the product which we are getting is good. You can also have some more salt. You can have more sugary taste. So these all type of information we can get back from the customer itself, and we can have a sentimental analysis, and this digital model can analyze that what type of actual processing needs which we can alter so that our product may be much more suitable for our end customers. So this is how a digital twin builds a link between a food factory to the customer itself. So we have started with a simple operation like a heat treatment to something, and we have ended to the feedback of the customers. All the things in digital twin is combined and connected. So even one end of the things changes, we can analyze what is the result in the other end. So we have more integration in each step of food processing using this digital twins. Okay, so this is a basic conceptualization which we can build smart factories in the future. Now we will see what are the applications of digital twins that the current industrial applications which we can see. So there are various digital twins that is already there in the market, like confectionery and food processing, like Mars Wrigley is using it to replicate the flow patterns, like that chocolate flow patterns, in order to know the inefficiency and optimize the process. Similarly, cold chain and logistics are using it to simulate the scenarios, how much time it will take to reach the end product, what type of quality of the product will be there if it reaches this time. So these type of scenarios can be simulated in order to get good quality product using digital twins. Apart from this, beverage industries like Coca-Cola is also using it for efficiently synchronizing their bottling facility as well as their like inventory services as well. Then multi-product food marketing manufacturing companies like Nestle is also using it. So they integrate data from like IoT-based Internet of Things-based sensor data and put it back to the monitoring dashboard in order to get efficient processing from where they started. Then industrial ovens are also using this in order to get the actual temperature that is needed based on the raw material quality which they are getting. So you don't need to like tune the temperature or basically get get the things done with the raw material itself, the temperature, like the oven itself, tune itself to get a good quality product. Like dairy processing is also using it with which can predict the line like fouling or the biofilm generation inside the processing plant. And large scale brewing like industrial brewers are also using it for dynamic recipe based on the models which they have built so far. So these are some practical, actual current industrial applications of digital twins, which we can see in the industry that has been implemented earlier. So it's not like digital twin is very new to us. This is already working in the industry. One more recent example I can think of is the Pringles is also using now a fully integrated digital twins that's we have conceptualized in the previous example, where they have their dough formulation, their machine parameters, and their customer feedback integrated. So if you say this type of Pringles I like more, so the actual processing line is going to build or tune the process according to that. So these are some current industrial application. It is already being used in the industry where we can see digital twin is getting good results. Okay. So every technology has its own limitation and challenges. So digital twin also have some limitation and challenges. First is because we are dealing with food, and food is a biological material. So there can be complexities and variabilities with the quality of product we are getting or the raw material we are getting. So we have to take this in account, and we have to make our model like that only. Secondly, food processing can be a very limited time process. So even a small change in temperature or time can be decisive in changing or altering the process itself. So it is a time-bound process. So getting real-time data and a good fidelity data, apart from this, a model with a higher fidelity is very important for us. Then computational models are very challenging because they need more and more computational power to run. As good result we want, we need to have more and more computational power. So we have to use ROMs and pins like reduced order models and physics-informed neural networks to get good fidelity results. Okay. Then there can be cost and cybersecurity. Since we are dealing with data in each from start to the end of the customer, we have to have a good command over the security of the data which we are dealing with. Then scalability and human acceptance. So still in India, I think most of the industry rely on human intervention. So we have to think about how much we can scale it and how we can turn this to actually improve efficiency of the food industry. Now coming to the end of this webinar, I'm now going to conclude this seminar. First is what we can learn from the seminar is we need digital twins in order to improve the efficiency. Okay. So a digital twin is not just a static thing. It is a dynamic thing that is getting fed with the data real time, and it is taking informed decision in real time. So it can actually improve the efficiency because it has flow of data, not just putting the data into the computer simulation software. Now, apart from this, we know that computational softwares and results can be time-taking process. So getting gray box models is at most priority. So we have to learn how we can integrate AI and computational model together. Then the ultimate goal of this is to increase the sustainability and improve the systems of system, like how we can connect various systems or various blockchains of our whole processing lineup. So these are some conclusive points of this webinar. I think I was able to impart the impression of digital twin and let you understand the concepts involved related to the digital twins. That's it for myself, sir.
Excellent, excellent. This Arpan.
Thank you, sir.
Very good, very well done. Job done. Now, just open to questions and participants. If you have any query, I think there are already in chat box 1 or 2 questions are
Okay,
there.
sir.
So,
Let me just please stop sharing.
well, Bandana,
there
you can read. Bandana can read.
Yes, sir. So there is one question from Miss Pragya. She is asking if you can explain about the scale vertically and horizontally.
Okay, so good question. What's the name? Pragya.
Yeah.
Okay, Pragya. So scaling vertically means like if you have simulated some unit operation, like if you have simulated drying process as such, okay? Now, if you are going vertical scaling, what you're going to do is you will now try to understand how the evaporation is going to take place. So altering the RH, how RH alteration can affect the evaporation process itself, how it can affect the diffusion process itself. So getting inside the product or at lower level is vertical scaling. Now horizontal scaling is more simple. It's simpler than vertical scaling. Here, if we have modeled the drying process, so we might have processed it beforehand. Like we have in case of some extrusion process, we do extrusion then drying. So scaling horizontally means we have already built the model for drying. Now we are going to build the model for extrusion. So now we can integrate drying and extrusion process. So this is called horizontal scaling. I think your doubt is clear.
Thank you, sir. So there is another question from Miss Vishwapriya. She is
Okay.
asking, in the steps of implementation, how can we define the decision boundary? Could you
Okay.
please explain again?
Yes. So defining decision boundary is very important, right? So we don't want our model to be over complicated. So what we want to do is we have to streamline the process. Suppose we are drying something, some product that is not that much, like RS fluctuation is not that much in our factory. Only the temperature is fluctuating, and due to that temperature, our product drying time can be reduced or increased. So we have to select which phenomena is the most important thing in order to get good quality of the digital twin. So here we are not going to take RH readings in our digital model because it will over complicate our model. In fact, we are only going to take temperature data. So this is how we can take informed decision in decisioning, like defining a decision boundary. It is the initial step of implementation.
Thank you, sir. So there is one more question from Mr. Vinu Sundar. He's asking, how can students start learning digital twins technology from their undergraduate itself? Could you please suggest some steps to get started?
Okay, so likewise, I have told you there it's not just computational modeling that is there in digital twins. It is also having some data-driven models. So you can start with some simple data-driven models. Let us suppose we have bananas, we have fresh bananas with us. Okay, now we have kept the bananas for few days. We are only taking pictures of this banana during the storage, and now till it gets spoils, we take the picture. And with this simple experimentation, we can build a model which can predict at what quality standard the banana is. Suppose your model can predict this banana is 10 days old. So this is how you can start building data-driven models. These are much simpler model because this doesn't involve physics. Okay. And secondly, if you want to build the computational models, these are much more difficult to build because you have to know all the physics and meshing and different type of operations that are in models. So for this, you can start with basic heat transfer in a cube. Like we have kept one temperature at one side of it at 20 degrees Celsius, and other side it has 40 degrees Celsius. So how much time it will take to stabilize the cube? So this type of problems you can start with. So this problem will help you in order to scale up your knowledge, in order to get the actual industry ready digital twin. So digital twin is the topmost layer which we are having. First, you can start with digital models, which we have seen in the first example, like milk boiling problem, which we are having non-dynamic static data. And you can also have some data-driven model like this computer vision type of problem. So this is the starting point of your experimentation with digital twins.
I think that Vinu Sundar is teacher or professor in some college, because this is very good, very interesting question, and even there is a role of both the teacher as well as the student. The teacher can give some sort of a few experiment which can easily be performed, and some models etc. has been explained by Arpan. So some entrepreneurship, short-term training program, etc. And this that students should be encouraged. So there is a obviously a student will learn, but there is a big role for UG students if you have asked. So here some role of the teacher also become very important, because it is the teacher concerned, a professor of the college, they should encourage the student and they should provide that opportunity to the students, all right, in the college, and if they tell them, yes, this is the thing and you can model this, then we get, and once they get one or two such examples and to get that benefit derived out of it, definitely it will pick up in the college. Now it is we are living in the social media era, so that is, but this is very effective. This may be very effective if provided and implemented in a proper manner. Thank you. Yes. Now next there is one more question, Vandana.
Yes, sir. Sir, there is one question from Mr. Homendra Kumar Shahu. He is asking if there is any free website which provide digital twin training.
Homendra, I don't recall any website that provides training actually to build digital twins. But since the digital twins itself is made from different building blocks, right? So you can learn data analysis, AI modeling, and computational modeling. And once you are good with all these skills, you can use it to integrate all these technologies. So you can learn chunks of the technologies, and then you can build your digital twin yourself.
So there is one question from Miss Pragya Arya. She's asking, can we use digital twin for iris cutter in bakery technology for dough cutting, like for infilled cookies or as per product dough optimization, so that during runtime dough does not show improper texture with heat like burst or crack of dough?
Yeah, that is very much possible, but it is a very difficult physics-based model. So first you have to analyze the actual physical condition, how your temperature and time affects your dough. Then the cutter speed and what is the actual force required in order to get the smooth surface. So all these things first you have to understand by yourself, because I suppose it is not being actually modeled previously. You might get good data for this cutter speed and the hardness of the dough itself, but few of the things you have to analyze. Once you analyze them, you can build a training based data for cutter speed and all, but you have to build a physical based model for your dough. So combining this, you can actually build digital twin, but it will not be an easy choice to do. If you are some doctoral student, I will suggest you can do that. But at BTech or master's level, what you can do is you can study the effect of cutter speed or the cutter pressure in order to get good quality, and you can build the data-driven model itself. So this is how you can proceed with your problem.
So think she can go for with that any process, but the important thing is that you have to have data for that. Okay.
Yes, data generation is important.
Data generation, and that too, as many large number of data if you are having, and then give your model will be good, perfect, right, can predict. So For any operation, first thing, important thing is that you have some physical data of that operation, and then go and use AI, use machine learning tools, etc. And give. I think that's so important.
Yes, sir.
So there is one question from Dr. Manikandan.
Yes.
He's asking, is there any scope to incorporate the management concepts of increasing efficiency in power consumption and cost cutting measures?
Yeah, this is very much possible. I don't recall all the scenarios, but I have seen few papers where they have scheduling the raw material supply and the fresh produce in order to efficiently transport the produce in good logistic way. So here you can use concepts of management and efficiency and power consumption together. The softwares like Schedule Pro that we have seen can be used in order to do that, I think. But it will basically depend on the problem and the choice, the choice of the problem you are going to deal with.
So there is one question from Miss Vishwapriya. She's
Mhm.
asking if you know any startups in India which are making digital twins for food processing.
Like in India, TCS is working on digital twins. Look, digital twins is a vast universe of the things. But in food processing, it's in India basically, its use is limited. As I told you, that companies like Coca-Cola, Mars, and even Pringles, all are using digital twins. I can't recall any Indian company as such. But in India, there's a large scope if you build some actual digital twins and can work with any industry in order to improve their efficiency and quality of the product.
Thank you, sir.
Any more
Uh,
questions?
Your,
if
your talk has generated a lot of enthusiasm. This is good, very interesting. So it is known by the number of questions you are getting.
Yes, sir.
Any other question, Vandana?
No, sir, that's all.
Good. So even the participants who are there, if, you can invite, if they can open, they can mute themselves, unmute themselves, and they speak if they can directly direct conversation if they want to have with Arpan Dubey. Any of you, those who are present, if you want to comment anything, you are most welcome. You want to speak, offer any suggestions. You can
Sir,
start.
thank you so much for the sir. Good evening, sir. Thank you so much for your amazing webinar, sir. Arpan sir, your talk was very inspiring, sir. Made us feel we can do so much. I asked that question because it sounds like such a daunting concept, this digital twin. So I asked for some basic steps. Thanks for breaking it down like that, sir. In next time in future, you could have a course. We'll start with a webinar like this and then we'll do basic steps, sir. That's my suggestion. Thank you so much, sir.
Very good, very good. Yes, that's exactly things. We are trying to do something. In fact, here in my lab, that some scholars are they are developing some digital twins for certain process, etc. And along with them, even some UG students are also getting attached with them, and they have to work. So that is how, as a teacher, you have to encourage them, you have to involve them, and once they are provided this, definitely it will come. And it is a very good. There is a vast scope of this, particularly the food processing industry, although challenging, because as I already
Hello.
been told
Sorry,
by
sir, my connection got interrupted.
honestly,
Yes, sir. Sorry, I missed something.
let's see, was Dr. I think Venu Sundar, she was telling that yes, she was appreciating your talk.
Okay. Thank you, ma'am.
If there is anyone else, if there is no more questions, can we wind up? Or any other participant wants to say something? Dr. Gupta ji, Dr. Yas Nikhil Gupta, I see him, sir. Would you like to say anything, sir? Dr. Yas Nikhil Gupta. Yes, Manikantanji.
Dr. Dubey, it's a very, really
sir.
it's a very illustrative presentation. I heartily congratulate for your exhaustive topic. Sir, my one humble suggestion: can you make one
Yes, sir.
model like
Okay.
like a rice processing or wheat processing? Anything if you consider any predictive that complete illustrative of this rice processing or wheat processing, so that it will be a
Okay.
good model for the students or learners to do the things, to learn the things. Okay, I think
Okay.
I hope you have understood my
Yes,
suggestions.
sir.
Yeah.
Yes, sir.
Yeah.
I'll try to build something, sir. And with platforms like H&M Food Pro Academy, I'd like to share that as well with
Yeah.
all of you.
That will be
So,
very good, great,
thank you for your suggestion, sir.
great things for.
Yes,
I
sir.
think, are you doing
Thank you, sir.
completed PhD or still? Are you?
He's a
No, sir.
postdoc. He has already
I've
completed.
completed my PhD.
Okay.
Yes.
Okay.
And he is waiting for your final. I think you are from ICR system, na?
Yes, sir. Yes, yes, yes.
So he has also cleared ICR net.
Oh, great. Welcome. Welcome.
Yes.
Two stages he has cleared.
Advanced welcome. Welcome.
Now interview is remaining, and he is
Yes.
one of very, very dynamic and most intelligent scholars in our group. That
Great.
did
Thank you,
both
sir.
MTech and PhD from our group at IIT Kharagpur.
Yeah.
Then it's
Good. Thank you. Thank you. Thank you.
Thank you, sir.
young mind.
Thank you, sir. Yes, ma'am.
Yes, Dr. Dubey. Firstly, I must
ma'am.
congratulate you for the explicit talk, and I'm happy you have
you.
developed some new technology. I wish you good luck.
Yes,
I
ma'am.
wish this new technology will have good prospects and bring us nice food products which are nutritious as well as low cost and have a good utility, not junk foods, but better technology used
Yes, ma'am.
for better nutrition products. Wish you all the best. My Ashirwad to yourself. That's what I
Okay.
would like
Thank you,
to say.
ma'am. Thank you.
Not
Thank you.
using
you.
any technology
Thank
at the moment because I am an elderly person, but I wish you good luck. Always have a good family and professional life. Thank you.
Thank you
Thank you,
very
ma'am.
much,
Thank you,
Professor
sir.
Sharma, for your nice words. Thank you.
Thank
आप
you.
लोगों का आशीर्वाद बच्चों के लिए बहुत जरूरी है.
तो जरूरी है जी, बहुत जरूरी है.
Good. Great.
Thank you. All the best.
Thank you.
Thank you, ma'am. Thank you, ma'am.
I think, Vandana, we can now the customary vote of thanks to our Arpan.
Yes, sir.
Thank you, sir, for providing me the platform to present myself. Thank you, sir.
That's great. That is done a great job.
Thank you.
Thank you, Arpan sir, for sharing your knowledge and valuable insights with us. And I would also like to thank H&M Food Pro Academy for organizing this webinar and all the participants for joining us and making this session interactive. Thank you everyone for joining us and have a wonderful day ahead.
Thank you. Thank you, everyone. Bye-bye.
Thank you.
Bye-bye.
Thank you, sir.